In this session, we will discuss radical expression written as rational exponents, as you see here. So on the exponent rules, there is a rule that they call fractional exponent, but is most known as rational exponent because the word rational means fraction. So exponent in the form of fraction. And you by now must be very familiar with this expression that we can rewrite our radical as a rational exponent, where the index of the root is the denominator and the power of the radicand is the numerator. Okay, so here I have some examples. So if you just look and observe, all of those expressions, they are rational exponents. So you know that each one of them represent a radical. And however, we will use the exponent rules because now the radical was rewritten as a exponent expression. And you have studied and be very familiar with the rules of the exponent. For example, this one here, I have my base is a rational, is a fraction with numerator and denominator. So I look here on the power of a fraction rule. What do I see? That I can distribute the power to the numerator and the power to the denominator. So is this that we're gonna use here. So we're gonna write 9/2 and 16 to the power of half. How farther can I go? Okay, so I know that this represents the square root of 9 by the rational exponent property. So I rewrite this back as a radical. And why am I doing that? Because I noticed that this is square root. And I see that this is a perfect square root in this as well. So if I can extract a square root of 9, I get 3, and the square root of 16 is a 4. And then so I evaluate this exponent and I see that the value for this exponent is 3/4, the most reduced steps. Let's do the same with the second one. I'm going to use also, so we have used this here and this here. Now let's use again the power fraction rule. So now I have 8, that's the numerator, to the power of 2/3, and 27 to the power of 2/3. I am willing to rewrite this as a radical because I see that this is a cube root, and cube root of 8 is perfect, and cube root of 27 is also perfect. And then I will rewrite this as such. Cube root of 8, but see that the numerator is 2, not 1 as this one. And then so I will write it as power of 2. And I do the same with the denominator. Cube root of 27, and the result of this to the power of 2. Okay, cube root of 8 is 2. So 8 is a perfect cube. But this result is squared. Here, cube root of 27. 27 is a perfect cube for 3. 3 times 3, 9. 9 times 3, 27. And I have squared. So here you'll be a 4, 2 times 2, and here is 3 times 3. So these represent the fraction for this simplified and reduced represent the fraction 4/9 is equivalent. Okay, now we're gonna see that we must apply a different exponent rule. An exponent that is negative. So negative exponent is this one. If I have a negative exponent, whatever is the base, I get its reciprocal. So then the reciprocal is to invert, but the denominator here is 1. So it means that would be 1, 25 halves. And now it becomes positive. And I can proceed because I see that this is square root and 25 is a perfect square. So then I can extract perfectly the square root of 25. I rewrite as square root of 25. Pay attention that my wrinkle has to be the length of the radicand. And this is equal 1/5. So simplifying this rational expression leads me to determine that this expression is equivalent to 1/5. Okay, let's apply another rule. So this rule is the power. So I have x, that's my base, to a power of half. And this whole thing goes to the power of 1/3. So it's the power rule. When I have a power rule, what do I do with the exponents? I multiply the exponents to increase, so it's a power rule. So I write the base x, and pay attention here, my rational exponent base was a numerical expression, just a number. Now I'm start to dealing with the algebraic expressions. So a radical expression can be in those two forms, just numbers, that's is a numerical expression, or use of algebraic expressions. Back here, so okay, this is my base, this is the variable x, and has the power half. That goes, the result goes to the power of 1/3. So then I multiply both powers. And I get x 1/6 is the result for this one. The next one I have two exponent expression, and they are multiplied. If they're next to each other with no symbols in between, is understood that there is a multiplication here. So if I have same base multiplying each other, what do? I apply the product rule. Same base, both has base A, and the exponents different or equal does not matter. What matters is that they must have the same base. I keep that base and I add the exponents. The power rule, I multiply the exponents. But when I have product of two exponents with same base, I keep the base and add the exponents. So I will write x 1/3 plus 1/4. And now you have, so you can use a calculator, or if you are very good with this, and then so you know that both have, you have to find a common denominator to add. So this goes a 4, this goes a 3, and here is 7/12. There is reduced, and then your x is to the power now of 7/12. And this is your final answer, because there is no way to obtain a value for it, because it's not a numerical expression, it's just an algebraic expression. So to multiply two exponents with same base, it results in one base, that's the common, and the null value for the exponent. So if you go use decimals, you go here and you write 1/3 plus 1/4. So you don't want the decimal value. You see the symbol here, you click here, then you have 7/12. And then you go back there and put the null power 7/12. Okay, the last one. The last one is we are talking about a quotient rule. Draw, and then draw. Okay, sorry about that. Okay, now we have same base. Pay attention, you can only apply those rules if you have exactly the same base. If you don't have same base, you leave as it is. There is nothing to be done. Here is you have a division, and I may represent as a fraction, but I know that the line between numerator and denominator represent division. So this is a quotient rule. Both exponents have same base. Yes, they do. X plus 1, x plus 1. And then what do I do with their exponent? I subtract their exponent. So I write the base x plus 1, and I subtract the exponent of the numerator minus the exponent of the denominator. And again, you can go straight. So here has the same denominator. So the answer here will be, so I'm gonna write here because I have to reduce. So this is negative 2/4 that can be reduced to negative 1/4. So the result here will be x plus 1 negative 1/4. Negative 1/4 is not a final answer because the exponent is negative. We always look to represent expression, exponent expression with a positive exponent. So then I have to come here and apply another rule again. So I'm going to apply the negative exponent. So I have to flip. I have to get the reciprocal of this expression. So if what I have here, will be 1 x plus 1 to the power of 1/4. And this is how you're gonna stop right here. Oh, 1/4, no. I have something here. Oh, I know where it was my mistake. When I reduce, this is a 2, right? Sorry about that. Divide by 2, divide by 2. And then I have negative half. And then becomes positive half. So then you stop right there. The null expression could be reduced, could be simplified to something that now contains only one exponent expression on the denominator. And then that's it. So you have to be very familiar. So you have to watch the previous video that go through the exponents, explain the mathematical reason behind those rules, because it's not a memorization of the rules, it's the mathematical understand of them that you immediately, as you manipulate those exponents, that you become more and more familiar with those rules. And the only rule that we did not use here, we didn't use 2 rules, this one and that one. For example, the zero exponent is a very, anything I have something x squared minus 3 to the power of 2/3, and all this to the power of 0. And then I would try to manipulate this and do so if I see that a base is to the power of 0, I don't have anything to do, because by definition, these represent 1. So this is an easy one that you have to remember. When is the power of 0 is always 1. Regardless what you have, as you can have the most complicated expression here. But when you see a 0, immediately you put as an answer 1. And then instead of a division here, if I had a multiplication, for example, x, y to the power of 1/2. I would write x to 1/2 and y to 1/2. Because the algebraic expression don't have anything to do. But if this was a number, and this is an expression, for example, let me give you a better one. For x to half, what can you do? You can write 4 to the half and x to the half. Can you do something with the numerical part? Yes, this represents the square root of 4. What is the square root of 4? Square root of 4 is 2. And then you have x to the half. Okay, so this is how you're gonna be faced with radical expressions represented as rational exponents, and what you can do. So once you treat them, those radicals as exponent, you can apply all the exponent rules.